Okay, welcome to the Learning Theory Spotlight session. Just a second. And the first speaker for this session is Chi-Cheng Zhang, and the title is Beyond Disagreement-Based Agnostic Active Learning.
Thank you. So I'm Chi-Cheng, and this is joint work with my advisor, Kamalika Chaudhuri. And so the problem we are considering is agnostic active learning, where we are given a lot of unlabeled data, draw ID from distribution, and we're given a hypothesis class. And our goal is to identify a classifier with low error with as low label request as possible. So notice that the problem we're considering is agnostic, which means that if the labels we query might not be the correct labels. So a major challenge in this scenario is to achieve consistency in general agnostic setting. And there has been some existing solutions to this problem. One solution is disagreement-based active learning, which works in general for general hypothesis class and data distribution, but the problem is that it's very conservative and have high label complexity. And on the other hand, they have the margin-based active learning, which has low label complexity, and it is very noise tolerant, but the problem is it only applies when you consider linear classification and the data distribution is isotropic log concave. So can we achieve the best of both algorithms? It turns out that in this paper, we propose an algorithm that gives a general agnostic active learning algorithm that have good label complexity. So for linear classification over log concave distribution, our bounds matches the margin-based active learning. And the major observation of our paper is that we reduce the problem of active learning into a confidence-rated prediction. So confidence-rated predictor is given a whole set of unlabeled examples, and you want to not only output plus labels or minus labels on the unlabeled examples, but sometimes occasionally output don't knows. So for those examples you output don't knows, potentially it is difficult to classify, so you want to do active query on that and perform refinements. So if the confidence-rated predictor satisfies some good properties, then our algorithm framework guarantees that this algorithm is consistent. And our reduction captures disagreement-based and margin-based approaches. And moreover, we can design a new confidence-rated predictor that have improved yield, label complexity results. So welcome to our poster 11 for more results. Thank you.
Thank you, Chi-Cheng. Next, we have Amir Sani, who's going to talk about exploiting easy data in online optimization.
Hello. Most online convex optimization problems are designed, or algorithms are designed for worst-case guarantees on hard data. Hard data is unpredictable, it's non-stationary, it's adversarial. So the problem with this is that in worst-case algorithms, they're generally over-conservative with easy data. Easy data is stationary, it's predictable, it's generally something that's much easier to predict. So it could be a benign adversary, for example. So when you look at the chart on easy data on the slide, you see on your left that follow the leader in green is log t, while hedge, worst-case guaranteed algorithm, is root t regret. This gap is quite large, but the problem is in hard data, follow the leader has linear regret. So you need the protection provided by hedge, which is this red line. And this red line, just to give you a point of reference, is root t on both charts. Now, the question is, can we get guarantees, upper bound guarantees in both easy and hard data where we can get close to these two levels? And this is something that exists in special purpose algorithms such as prediction with expert advice, online convex optimization, multi-arm bandits, but the algorithms are generally very complicated, very difficult to analyze, and not very versatile. So it's not something you can understand and then just map over to a new setting. You need to do something that's much more complicated and ad hoc. So in this paper, we present an algorithm that's versatile, very simple to understand, and what it does is, and the algorithm is called AB-prod, and what AB-prod does is it smoothly mixes predictions between an algorithm A with worst-case guarantees and a benchmark B that exploits the loss structure within the data. And in doing this, it simultaneously upper bounds the regret on easy and hard data, so that your regret is upper bounded by the benchmark plus 2 log 2, and at the same time, the algorithm A with worst-case guarantees plus a factor of root t log t. The algorithm is general purpose, it's interpretable, and it's very simple to understand. It's so simple, in fact, that we can recover the guarantees of adaptive online gradient descent while also solving this year's cold open problem in tracking the best expert. At the same time, in this paper, we also present prediction with expert advice and two-point banded feedback as two other applications in which we can actually show the application of AB Prod. So if you'd like to learn more about AB Prod, please come to poster 13. It's very simple. If you have any problem with worst case guaranteed algorithm A and some benchmark that can be opportunistic B, you can use this algorithm to get the kind of guarantees we provide. Thank you.
Thank you, Amir. Next we have Sheffet, who's going to talk about learning mixture of ranking models.
Can everyone hear me? Okay. This is joint work with Pranjal Awasthi, Blum, and Aravindan Vijayaraghavan, and I would be remiss if I didn't mention that both Pranjal and I are currently on the market. And I'm talking about learning ranking, highly applicable, well-studied task in machine learning, often also studied from the probabilistic viewpoint, where we assume our data, our sample of ranking, was sampled from some distribution. Most common of those models is the Mellows model. The probability of seeing a ranking pi is proportional to e to the minus some constants to the power of the distance between pi and pi star. Pi star is sort of the central ranking, the one that we as a population agree on the most. And indeed, if you have large enough sampled from a single Mellows model, you can learn the parameters of the problem. It's not complicated to see. However, what about mixture models, where you have two models of a Mellows model? For example, men and women vote differently among the different alternatives. I want to emphasize that prior to our work, it wasn't even known if the mixture model is identifiable. That is, the distribution it induces over ranking is unique. So not only we solve the identifiability problem, we also give a polytime algorithms in all the parameters of the problem to learn any mixture of two Mellows models. And I do mean any mixture, without any condition like independence, separability, or whatever. A word about our algorithm. It uses this technique of third order tensor decomposition, which does work conditionally based on independence conditions. So whether it succeeds or whether it fails, our algorithm still needs to do a lot of work. However, the more important point is that this is a ranking model. It's not a priori clear what are the equivalent notions of moments here. And pretty much all the basic attempts to try and find moments here in this probability model don't work and don't give you any reasonable notion of moments. What does work, and it took us a while to discover, is the following notion of kth moment, where the probability of any k items to be ranked as the top k choices. For example, here, probability of elements i, j, and k to be ranked as the top 3 elements. And I do mean top 3 as a set, not I in first position, j in second position, k in third, as a set. These are more preferable to the other n-3 elements. Come and talk to us in the poster session. Hope you, if anything, you remember this equivalent notion of moments, because I think you can leverage it on it if you're doing any other work on Mellows model. Thank you.
Thank you, Or. And now let us welcome Andres Munoz Medina, who's going to tell us about optimal regret minimization in posted price auctions.
Hi, thank you, Vitaly. I'm going to be presenting some work that I did with my advisor, Mohri. I'm hoping I can explain all of my work with this little comic. So here you can see a guy that wants to buy a plant, that he has some valuation, that it's $2. And you can see that the seller, who doesn't know this valuation, wants to extract as much revenue as possible. So after a while, they start bargaining. Somebody offers a price, the other one says no, and blah, blah, blah. And after a long time, they finally agree on selling $2. Unfortunately, a lot of time has passed, and now the plant is dead. So if the seller had known the valuation of the buyer, he could have saved himself a lot of time and still made the $2, right? So just as a plant seller, my goal is to learn the valuation of a buyer for a particular object. And I know what you're thinking. Selling plants is really profitable. But my main idea for this problem comes from selling online advertisement. In particular, I'm thinking about ad exchanges, where millions and millions of transactions are done every day. And you can think that if you have all of this historical data, you could try to leverage it in order to get a revenue optimization algorithm. However, if the buyers know that you're running a revenue optimization algorithm, they would react against it, and they would probably lie on initial interactions with this algorithm in a manner of obtaining better prices in the future. So I'm going to model my problem as a game, as a repeated game, where the seller has a revenue optimization algorithm, the buyer knows that optimization algorithm, and can act strategically against it. This should remind you of adversarial learning, except that, and there are several regret minimization algorithms that we know. However, if you come to my poster, I can show you that the notion of regret, or the standard notion of regret that we know, is meaningless for this scenario. And so a question becomes, can we give a meaningful definition of regret for our problem? The answer to this is yes. However, because the buyer knows my algorithm, in order to evaluate this regret, have to look at the whole decision tree that the buyer induced, right? Studying that, you can already see that it's hard, and it's really complicated to find an algorithm that minimizes this regret. So the central question that I try to answer is, can we actually minimize this regret? And is the minimization of this regret is going to be sublinear? The answer to this question and to other questions that arise from this problem can be found on my poster, and I welcome you to come see it. Thank you very much.
Thank you so much, Andres. And now we have Kamalika Chaudhuri, who's going to tell us about rates of convergence for nearest neighbor classification.
Thank you very much. I'm Kamalika Chaudhuri, and this is joint work with my collaborator, Dasgupta. So we all know the nearest neighbor classifier. It's a very classical algorithm. The idea is that you look at for every data point, you look at the k closest neighbors and then take the majority of their labels. So in this paper, what we look at is how to characterize the rates of convergence of such classifiers. And so what is the risk of a nearest neighbor classifier? Well, it's the risk that it predicts the wrong label. And what we do is we compare it to something called the Bayes optimal classifier, which essentially measures how well you could possibly do. And what we would like to know is how this risk relates to the risk of the Bayes optimal classifier, R star. So, as it's a classical algorithm, there has been a lot of previous results on this problem. A lot of results have looked at consistency in a very asymptotic sense. So what happens when n tends to infinity and k also tends to infinity together with n. There have also been a lot of rates of convergence, but they always, most of them, they always depend on smoothness assumptions. So what do I mean by smoothness? So what they mean is that the density, either the class conditional density or py given x is somehow changing, it's not changing very fast. However, what we find is that a lot of these rates of convergence results do not match practice. So there are various practical cases where k nearest neighbor works extremely well, but this is not predicted by these rates of convergence results, and this is the starting point of our work. So just to give you an example, in the picture that you see over there, the densities are not smooth at all. And however, provided this gap is large enough or relative to the various parameters k and n, what's going to happen is the nearest neighbor is going to do fine for this example. And this is the starting point of our investigation. In our work, what we do is to understand this phenomena, we introduce a new notion of an effective interior and effective boundary. So we say that a point x is in a p delta interior if a ball of probability mass delta. So the thing to notice is a ball of probability mass p around it has py given x bounded away from a half by delta. And what we show is that if x is in the p delta interior for p approximately k over n and delta approximately 1 over square root k, then nearest neighbors would work well for x. Whereas if it's in the boundary, then, according to this notion, then nearest neighbors won't work as well. And using this notion, we can get a whole series of results. We can get a new set of convergence rates. We can get universal consistency in very general metric spaces under certain conditions. We can get lower bounds. We can get smoothness conditions which are tailored to nearest neighbors, and we can get margin bounds. So come by our poster if you would like to know more about this work. Thank you.
Thank you, Kamalika. And now we have the final talk of this spotlight session. It is given by Michal Derezinski, and it's on the limits of squared Euclidean distance regularization.
Hi, my name is Michal. In this paper, I worked with Manfred Warmuth to demonstrate a simple learning problem where we give the solution explicitly as one of the features, and yet it is still hard for any kernelizable algorithm. Consider a random square plus minus 1 data matrix where each row is an instance, and we pick one of the feature columns to represent the target labels. Now train on a subset of instances and test on the entire data set. Clearly, there is a simple linear solution. Just take a unit vector with 1 at the right coefficient and 0s everywhere else, and you get the target feature. We look at a linear classifier like logistic regression or SVM. If you train it with gradient descent with two-norm regularization, then the predictor W is a linear combination of instances, which is what enables kernelization. However, there's a trade-off here, particularly for sparse problems like this one. We prove that those algorithms, with or without kernelization, provide virtually no generalization in this case, which you can see in the solid red line, plotting the loss against the size of the training set. Recall that the training set is included in computing the loss, hence the linear drop. On the other hand, if we add one-norm regularization, we break the kernel paradigm, but now we are able to learn this problem. That's the dashed blue line. The green line represents the exponentiated gradient algorithm. The proof technique that we use for the hardness result is based on estimating the rigidity of a random matrix with respect to its sign rank. For more details, I refer to our poster number 46. Based on some experimental evidence, we conjecture that the problem remains hard for deep neural nets with similar training assumptions. Different transfer functions like rectifiers don't help, and dropout also doesn't. However, one-norm regularization does address the issue. Thank you.
Thank you, Michal, and that concludes our spotlight session.